Hi, let's talk about plumbing today. So we've just concluded our HVAC section, and now we're going to be talking about plumbing, right? So let's get down into it. So plumbing system design. This is week 6, right? So now plumbing basically consists of um piping, flow, um friction, and a lot of things. Yeah. So now to get your water supply design, there's water supply, there's also water drainage. So this week we talk about water supply, right? So water supply and design ensures that every fixture receives adequate flow and pressure, right? Under peak demand without excessive velocity, which leads to noise or erosion, without oversizing, which leads to high cost, and without undersizing, which leads to poor performance, right? So now if you ever have been in a building where you turn on the tap and it's flowing less than it should, you know that the pipes are not sized properly. Or when you turn on like multiple taps at the same time and then you see that there. I mean, sometimes when it's just that tap that's on, you will not notice like the underperformance, right? But by the time you turn on multiple taps, or yes, for any reason, a lot of taps are in use at the same time, you see that the flow reduces, or you turn on the shower and the shower is not flowing properly. That is low pressure, right? So let's just get into it. So that's usually as a source of that is usually as a result of um poor plumbing design, right? So now a complete water supply design answers 4 questions: how much water is needed, the volume of water needed, um how fast must it flow. This has to do with the velocity, right? So depending on the particular type of fixture, it to determine the amount of water that is needed in that particular fixture, right? So then also the pressure. Some some fixtures require more pressure than others. A shower, for example, right? And pressure is also important because sometimes the water will need to like travel a vertical distance upward, and if the pressure is not enough to be able to do that, travel that distance, right? And also pressure is necessary because it helps to prevent over pressure or under pressure, which could damage, or which could over pressure could damage the system, and under pressure, or let me speak correct English, right? um Excessive pressure could damage a fixture, while um insufficient pressure could result in poor performance, right? Then the equipment needed to deliver. So there's different equipment that is used in like plumbing design, right? So yeah, so let's go on. So now we talk about water supply demand. Oh, supply and demand in the same place. It's quite crazy, right? But it's just supposed to be supply, right? Water supply and fixture unit, right? Calculation. So this short form is WSFE, right? So it is a standard method for estimating the water demand for a building. Okay, this demand, that is where that came up, right? So the system assigns a value called this to each fixture in a building based on the amount of water required and the frequency of use. Emphasis on the amount and the frequency, right? The frequency. So the account, and you know that obviously in commercial buildings the frequency is way higher, right? Or the amount is way higher than in a residential building. So the demand is usually higher as a result. So the account for intermittent use and or simultaneous usage. I also mentioned when you turn on multiple taps at the same time, or multiple plumbing fixtures at the same time, and then the system may not be able to meet that demand, right? So it's important to understand this for each different system so that you can um understand how to size accordingly. So now I know that I mentioned calculation, right? But thank God for advancement. A lot can be done by reading your values from tables, right? So let's quickly look up what this. So now to get the code, or rather like there are standard codes that we use, right? And then these standard codes help us to um gives us the standard values we need, right? So let's quickly look at them one after the other. And so first, let's look for IPC 2024. IPC stands for International Plumbing Code, right? IPC 24 is the latest version of the International Plumbing Code, and we're going to look for this particular table, and it's going to show us what the code says about WSFU, right? Okay. This is basically what the code says. So simply paste that into your browser, and it will just help you to look up that particular table you're looking for. So you can see here that we have different types of fixtures, right? Or group of fixtures too, and then the WSFU values. Basically, each of them has a value assigned to them based on the type of thing, right? Type of fixture it is. And if you notice, let's look at, so this is the lavatory. The lavatory has a quite low value because the flow in the lavatory is not so high. And we have kitchen sink. Kitchen sink, you may think that kitchen sink and lavatory supposed to be around the same value, sure. But most time the kitchen sink usually has like higher demand because a lot of washing going there. Whereas lavatory is usually like just that bathroom sink that you just when you're in the bathroom you use it and you don't use it that much, right? And then if you notice too, there's the hot water side and the cold water side. Not everyone has both. So let's see. WC does not have hot water. Those big two is just like a tap, just a regular tap, right? Doesn't have hot water value. But the rest, all of them always have cold water. Okay, right. You can see here that we have dishwasher, which uses only hot water, right? And then this is combined, right? So we'll look at this again when we are like designing for a plumbing project, right? So let's move on to state PC now. So now this international PC is like the name implies, it is like a standard that the international body uses, right? But then in the US, each state has a particular plumbing code that it's usually based off of the international code, and then just that little changes can be made in that state code to just to match their reality, to match their conditions, right? Just like how you have um just like how you have like maybe earthquakes and more in a particular location, so the structural code will be different from that place. Or you have maybe different temperatures, like climate temperatures in a particular location, and that can affect, for example, like something as little as maybe the insulation specification for a pipe. So those are some little things. So in as much as you check the international code, if you need to design for this, now stands for Florida plumbing code. So you just, if you need to design for a project in Florida, you just need to look up this table in Florida, right? There might have been some slight changes that they applied for a reason. Then this one starts for South Carolina plumbing code, right? Another type of code, or another code that is used, it is also uniform plumbing code. So you can always look this up. And then you have California plumbing code. California is a state in the US, but they don't always use the same um, plumbing code as the rest of the states, right? So for reasons best known to them, right? So in a lot of cases, the values you have here, I mean, they are close because I mean anything that works in one place works in a lot of other places, but they have some strict measures, right? So now to get for California, you now have to look up this, right? Let's look for what it looks like. California plumbing code. I think I searched it up already somewhere. Okay, is this it? Okay. And even the way the code is shown is a bit different, right? Okay, this is it. So this is 2022. I think their latest code is 2025. So let me see if I copied it. Let me copy it. Right. Okay, let me look for their latest 2025. Right. So CPC doesn't use it doesn't use it's not really based off of IPC. So the format, everything is completely different. right? So you just look up this table. So this is what it looks like. Then this is the table of, okay, let's close this. This is the table of content, and I'm looking for chapter 6. This is the different chapters. Okay, chapter 6, 610. Looking for 610. Right. You can see, you can always go through all these values to check details of plumbing in that city or in that state. Okay, this is what I'm looking for. Okay. Okay. So I can zoom in here. Then, right, you can see now that this gives us an idea of the WSFE for different fixtures. So let's continue. So now we've talked about WSFE. That just basically gives us an idea of what the demand in those features look like, right? So now let's talk about pipe sizing, another important aspect of plumbing design, right? So now if you remember continuity equation, right, this has to do with um conservation of energy, right? And that means that basically um for any quantity of water or any quantity of flow in a pipe, it usually applies for pipe flow, right? Quantity of liquid in a flow. The relationship between the area and velocity is such that the product at one side at a particular like area one, I think we need like we need what they call it, we need a bit of illustration for this. So okay, I was just looking at, oh no, this is not what I want. Okay, as you can see here, we have the volume. So when the volume is bigger, the flow, the area, sorry, when the area is bigger, the velocity. Okay, it's a relationship between area and velocity. So for a smaller area, right, the velocity is higher, and therefore a larger area, the velocity is lower, right? But at every point in time, the values might change, but the same quantity of flow is flowing through two of them. So once you, the whole point of this, why this is important is because when you're sizing, right? If you're sizing for a bigger building, you know that the quantity of water needed is more. And that also means that you're going to need bigger pipes, right? So if you use a smaller pipe, you will need the velocity to be really high to match the volume of water needed in that space, right? So that's why it's important to size accordingly so that you don't have a case of having less than necessary. And obviously, when you have like more velocity than you can carry, that also brings pressure issues too. And then it can also like destroy some certain um, um, fixtures, right? Although high velocity is also good because it helps overcome friction, right? So that one is usually better when you have to deal with like long distances, right? So that is why you need to understand this, right? So you just need to do like extra reading to understand it better. Okay. So now see in this section, you see pipes must design objective here. So now when you're designing for a project or for a building, the pipes must be able to carry the design flow, right? So that's the amount of water needed that building. Then it must be able to maintain the required pressure, right? Because it tends to drop, pressure tends to drop over time, right? Or not over time, over the distance, right? Okay, pressure does not really drop over a distance. There are different forms of pressure, right? There's static pressure, there's dynamic pressure. So it doesn't really drop. Static pressure is that is not like the okay, let me just talk about it because I've mentioned it, right? Static pressure is like the pressure at a particular like point in a pipe, right? And the higher the velocity of the flow in that pipe, the lower the pressure, the lower the static pressure, right? So then the lower the velocity, the higher the static pressure, right? So that just means that understanding the pressure velocity relationship does helps you to like design better, right? So now staying within the velocity limit. I also mentioned how high velocity can cause damage, right? And also, in as much as it shouldn't be too high, it should also be high enough to be able to like carry over the distance, right? So most times when you talk about distance, is that velocity that might not be able to go over that long distance because of friction losses, right? Which makes it to reduce the velocity over time, right? So then I just talked about the friction loss, right? So next, let's talk more about velocity limits, right? So select slightly bigger pipes when sizing hot water lines, right? If you remember from science, chemistry, or physics classes, anywhere that heat is involved, it always brings another like dimension of reaction, dimension of um results, right? So whatever you do, by the time you introduce it, either it speeds it up or whatever, right? So there's higher chances of erosion, right? Because of the high temperature. There's also possibility of noise, and then pipe degradation. These all go together pretty much. So when sizing for hot water, it's usually advisable to select slightly higher. It's just that in some cases, right, it may not be significant differences, right? If you use a 3/4 inch pipe for cold water, right? If the distance is not so much, 3/4 still works for hot water too, right? But in cases where the distance is so large, right, you now need to increase, although the difference is not so much all the time. And besides, this usually works for when the water is very, very hot. When you're designing for like cases where the demand of hot water is very high, which is not in all cases. So this is just something you have at the back of your mind, even though you may not use it all the time. So if it's just a small, low temperature, maybe 120 degree Fahrenheit, right? You may not need to. It's only when you need to like you have like higher demand at higher temperatures, right? So now moving on. So pipe sizing. Now, pipe sizing, let's go down into it, right? So first of all, you need to determine the total WSFU. Right? Let's look at the project that I want us to work on today. Okay, no, okay, let's look at this one. Right. I might not WSFU. I might not go into detail into this class, but subsequently I will, right? Okay. So now this, I got this from this particular table, the one we just looked at. This is the California project, right? So you see the different, I listed out the different fixtures. You look at your project, like your architectural plan, you have all your fixtures on plan, right? And then the ones that are not indicated, they'll probably be in the document somewhere where it is indicated that this is there, right? So it's important you also ask questions ahead of time too. If you're not clear, right? There was a project I worked on where they didn't have like all the fixtures on the page, and then I had to like get feedback on that, right? So you see the quantities, then you see the WSFU, which we read from this table, right? And you notice that for something like WC is quite high, right? Then for lav is quite low, lavatory is quite low, and then sink and tap. I modeled tap like a sink because I couldn't find values for a sink, right? And also this was that my winery project, right? So there were taps that required both hot and cold water, right? From what they gave me, the clients, the project information, right? So you notice that there's the CW, which is cold water, and then there's total. This one takes note of the quantity of fixtures, right? So in this case, it changes because there are five of it, right? Then the hot water too. You see, WC doesn't have hot water, but the rest do. So that is why you get your total HW or total WSFU, right? For your hot water and then the total altogether. So the whole point of this specifying this table, this is my page one, cover page of specifying this table is later for this pipe sizing, right? So you take this 12.5 and then you go to, that's your total WSFU. You go to your select pipe material, right? So in many cases, I use copper, although in some cases, you may have to specify a different type of material, right? So these are like all the different types of material available, right? So then go to the sizing table, which is this. Okay, this is a California project, right? So let's use the California um this thing, right? Okay, let's not talk about it now. I mean, while I'm okay, let me just show you like a glimpse. Then later when I'm doing the project, you understand it better. So let's look for this table, right? Looking for six. Okay, so this was 10.3, right? So what we are looking for is 10.4. Okay, perfect. I don't need this. So now I'll just take the readings, right? This is the different sizes. So it's basically just go here, look for the maximum length, right? In your maximum distance of your farthest fixture, you measure the distance, right? And this is them in feet, right? By the way, US uses feet and inches as opposed to the metric system that you might be used to. So measured in feet. So let's say 100 feet, for example, is the farthest distance away from the water meter, right? So this is this. And then we saw that our total WSFU was about 10 points. Okay, let's look at it again. That was, okay, 12.5. So now you go here, 100, then this is 12. Look for, this is what the WSFU value is. So now 12.5, I mean, we could easily go to 21, but let's just stick here because it's still very close, right? But the way this works is that you're supposed to take, this is supposed to be the maximum value for this row. So once it exceeds, if it gets to 13, you go to the next row, right? So being that is a very small difference, and then I didn't want to, let's just use this one. So now we trace it back here and see that the size of our pipe that can carry this load, this demand is 3/4 inches, 3/4 inches. So this is the meter size and this is the building size. This is the main supply pipe in the building. We'll talk about this. That this is just an example, right? So let's move on with our calculation. I mean, if you go to this table for, let's go to this table. So I just have a glimpse. This table for, what do you call it, for IPC, right? Okay, this is our appendix, right? This is 2024. So let's go down. Basically, there's a lot of information on this page on how pipe sizing works, but because you don't have time, you can always look this up in your free time, right? But we don't have time right now. They talk about fittings, pressure, and fittings loss, friction, and all that, right? Okay, this is this is a similar table but for IPC, right? So you look, you see it's very similar. You have 100, you have about 12. So you go here, this is where it fits in, and then you see it's actually quite close. The pipe size is quite close, right? 3/4 1. And you see that one that I skipped before because I was trying to save on. I was trying to save on. I don't want to oversize too much. 12.5. I said let me go with 12. You see that in this case now it must be 1 inch, right? So let's move on. Right. Okay. Okay. Moving on. So when you do all of that, you'll be able to get your pipe size, right? So the whole point of this pipe size is just so that you can size correctly, right? And then as the pipe branches out, obviously, just like how when we are doing for ducting, when it gets to a distance, right, the distance reduces. That's as the water travels to the end. It gets to a point where the distance reduces, so you have to also reduce the size of the pipe at that point too, right? So basically, just to prevent like oversizing issues. Remember the continuity equation where we talk about how area has to meet velocity. So sometimes you need to reduce the size of the pipe so that you're able to maintain the velocity, right? Because velocity tends to drop, right, over the distance. So you to when you reduce the area, you're able to like get the velocity back up too. So and then you also save cost by not oversizing and not stressing the plumbing system. So next, talk about um, adjust the diameter accordingly. This is just what I just talked about. Right, so next we talk about hot water system design considerations rather. So this one is something that you need to like you understand it more with time as you design more. So now when we are designing for hot water, right? So we talk about simultaneous hot water demand. So usually for regular pipe sizing, I just take a total of the WSFU, right? Which is this. This is the total, right? And then I size with that total because in as much as it's rare or almost not possible for all taps to be on the same time, right? But it's still very possible. I mean, in engineering, we do factor of safety a lot, right? So we factor out the most um, the most insane possibility, right? So there could be cases where all the taps are turned on at the same time. So it's good that you are sizing your system for all the fixtures to be able to meet that kind of demand, right? And that's what I do for regular cold water sizing. But for hot water, is a bit different, right? I mean, the tendency to turn on all hot water, for hot water to be needed like all at the same time, the tendency is way lower. So for hot water, I tend to just focus more on like the fixtures that are needed at the same time, right? So I mean, it's still possible to size for all at the same time, right? But this just make your design to be a bit more economic, right? And it's usually more for tankless water heaters. We'll talk more about the types of water heaters, right? So next, talk about temperature requirements. So for residential buildings, it's usually around 120 degrees Fahrenheit, and then for commercial buildings, it's as high as 160 degree Fahrenheit. So this is mostly because of hygiene standards, right, which are needed in places like maybe kitchens, commercial kitchens, or hotels, then health facilities too, basically, because these places need like high standards, right? And then hotels, then hostels too, right? So basically, the standards are way higher for commercial buildings, right? I mean, if it's not so high, you can settle for like 140, right? If the demand, if the building is not that type of building, but it can be like 140, right? But 160 is like a maximum value, right? Anything higher than 160, you're already talking about doing like maybe industrial design, or you're probably designing for like something special, right? So we also talk about temperature drop. So now temperature drop is important when considering sizing water heater, sorry, sizing hot water systems, because um, if because of distance, for example, it's not just velocity that drops. By the time the temperature, you remember heat exchangers, by the time it travels a certain distance, right? Even if it's insulated, it's worse if it's not insulated. But if the pipe is not insulated, it loses temperature over that distance, right? So it's something that I also need to take into consideration, right? And then if routing preferences, because I like to route my pipes within interior walls, right? Because if the pipe is an exterior wall, it interacts a lot with the external climate, or the outdoor temperature, right? So if the outdoor temperature is very cold, the water in the pipe tend to freeze, and then it loses a lot of heat, right? So that's where routing preferences. So if I have to route a pipe that is containing hot water, I really don't like to pass it as in an exterior wall unless I don't have a choice, right? Then also insulation, pipe insulation too. So you need to like understand how all this works. Then let's talk about recirculation. Recirculation is one of the solutions to temperature drops, because by the time you have a for a large building where the pipe length between the water heater and the farthest fixture is exceeding 50 feet, you need recirculation. This is just saying that this is the maximum. Once it exceeds this, the temperature drop would have been so high that it's almost not even hot water anymore. It doesn't meet what is needed for that fixture at that distance, right? So we talk about how hot water recirculation loop is going to be added to the design, and then it helps to reduce the wait time, so that when you turn on your hot water tap, you get your hot water almost instantly, so you don't have to wait and then waste water, and then or waste energy. And then it also improves user comfort, so that time of waiting and that temperature you need it at it's got instantly, you feel better. And then it also helps to meet code requirements. But I know I mentioned about energy standards in one of our past HVAC classes. So this is one of those energy standards, because it's basically energy as to heat your water, right? So recirculation design usually involves return piping. So remember the loop we talked about here. The loop is because it forms a loop. So as the water goes forward into the particular pipe, it has to like return through another pipe, right? Which forms that loop. So you also need to consider this. And then the recirculation pump has to be able to cater for the demand, the flow rate, the distance and the pressure too, right? So balancing valves and temperature control, you also need to understand this, right? So these are the two that is mostly shown in your design, but these also need to be added in notes, right? So let's move on. So next, pressure requirements, right? So pressure requirement is a bit tricky, right? So you have minimum pressure at fixtures, because if you give it more than it requires, I said it before, when required could damage it, but if you give it less than it requires, it could result in poor performance. So now this is another table that we use when talking about pressure, right? We see it is still in this IPC, right? So for a lavatory, it has a minimum pressure of 8, a shower, a minimum pressure of 8, right? Let's look for this table. This 604. Let's look for this table. So this is our table, 604.3. This is IPC 2024. Okay, perfect. So you see the different flow rates, right? And then you see the PSI. This is the pressure rating. Right? So you see that, but though these are just the minimum, though this could work at higher pressures. And you see a lot of them at 8. And then cases where it's higher, it's usually just stuff with these. And this is shower, like I mentioned before. This is other types. You see, this also requires a shower too, right? So let's go on. Now there's something about this is for IPC, right? But for CPC does not have a specific table. That's why I say that it is a bit tricky, right? For specifying the operating pressure for the fixture. But this section CISO 8.0, it indicates a minimum of, that is in CPC, right? It indicates a minimum of 15 psi and a maximum of 80 psi, right, for plumbing fixtures, right? So let's look at what this says about plumbing fixtures. Let's go to CPC. Okay, 604, 608.0. That is okay. See the water pressure I spoke about. You will notice 15 pounds psi, and as a minimum. Okay, this is excessive. Maximum should not exceed 80, right? So in most cases, this is part of when I spoke about how um, California Plumbing Code tends to deviate a little from IPC, right? But most times, what works in one works in the other because it's the same planet Earth we are on. It's just that these ones have like more stricter standards, right? So I believe that these are the minimum. But if you use your shower or your lavatory at 15 psi, for example, it will still work, right? So this is like a safe minimum value across all, right? But it's still necessary to consult your codes when you're in doubt, right? They are what guide you, right? So and then you can like go up to like 20 psi or 30 psi for um fixtures that need higher um pressure ratings, pressure levels, right? So I generally don't include my pressure table when I'm calculating for any California project, right? But in other projects, I tend to put it because they are like specific values stated, right? Because it's a minimum, right? So let's move on. So pressure loss, right? I've spoken about this like a couple of times over this class, right? So now total pressure loss includes, like why we talk about pressure a lot is because pressure tends to change over distances, right? So and then as you go, this is as you go over the, you see here, according to elevation, as you rise up, as the pipe goes up vertical distance, pressure is being lost, right? And then because of horizontal pipe length, pressure is being lost to friction and maybe fittings, right? Along that pipe length, right? These are different types of fittings. We also talked about this in HVAC, how the fittings have to have like affect the flow of air. So even the flow of water, this is still fluid dynamics, right? So all those changing direction, changing dimensions, cross section, and all of that, it affects the pressure differences, pressure gradient, right? Then even when the water flows into like equipment or filters and backflow preventers, we'll talk about it shortly. It's all these different, anything that basically affects the natural flow will affect the pressure level, right? Then residual pressure too. This is the pressure, the minimum pressure needed under a particular fixture. So at the end of the day, whatever the pressure has faced, the pressure level entering this thing has faced, it should be able to match. So it should be able to meet the pressure, minimum pressure needed for the fixture, right? So this is why the understanding is necessary, right? So next, talk about solutions to pressure problems. So whenever if you pick a smaller pipe than necessary, you have pressure challenges, right? So you may need to upsize. Then if you pick a pipe that is, sorry, pressure booster pump, this usually is used when pressure is lower. Maybe you need pressure to go like vertical distances up to like stories, right? Or you have like longer horizontal distances, right? Or you need higher velocity or higher demand, right? You may need to include your pressure booster pump, right? So anything pump goes with pressure, right? So and then sizing it usually requires the height you're sending it up to, the velocity supposed to flow at, and then or the flow basically, and then the demand, right? This is like these are like the basic parameters you need to size the pressure pump, right? Then also zoning the building helps, especially for hot water. So zoning the building is just like zoning for HVAC too. Zoning the building helps when you know that the different zones. For example, now you have um um maybe a kitchen right on one end, and you have like maybe apartments on another end, right? So if the distance is so high, you may even need to create different zones, and then you work for different parameters for those different zones, right? So, and then reducing excessive fittings, right? So this is very important, right? Even what you are like doing your layout, your drawing for your piping, let's don't have too much fixtures, right? Because this is going to affect your pressure and your velocity and everything, right? So those little changes is what add up to big changes. So now let's talk about sizing, right? So first talk about water heaters. So now let's talk about the different types of water heaters. Okay, let's talk about the how water heater demand is calculated, or how it works, right? So we have both in GPH, which is gallon per hour, and GPM, which is gallon per minute. Now, when I'm sizing, I usually prefer selecting. There are two types of water heaters. There's the tankless and there's the tank water heater. Tank water heater is the one that has storage unit, right? Tankless does not have storage unit. It just has heating elements. So that when the demand is the water passes through, gets heated up within a short period of time, and then it is delivered, right? But for tankless water heater, it is I don't use it much unless it is requested for, because it tends to have a very high energy consumption. So while the other one heats at a lower rate, so it needs like lower energy per time, and then it stores that water, right, in a insulated tank. In an insulated tank, this other one does not use that tank, so it produces it on the go, right, on the go. So usually when I'm sizing for tank water heater, I use GPH because I'm sizing over like a larger period of time, like a long per hour. But for tankless, I use GPM, which is over a short period of time. That 1 minute, that's gallon per minute, right? So we'll talk about that as we move on. So then you also, another thing to consider when sizing water heater is the temperature rise. So remember we talked about how there are different temperature requirements for different types of buildings. So obviously, if the temperature, groundwater temp, and then also groundwater temperature for the different locations varies too. Be 60 in one place, 60 Fahrenheit in one place, be 40 in a colder region, it could be 80 in a hotter region. So when you understand the temperature needed and the temperature available, that gives you the temperature rise. Now, another thing to talk about is storage versus installation. This is what I just talked about, tankless and tank. So the storage goes with is the tank water heater, and then because the tank is for storage, and then instantaneous is tankless. So it does not need a tank. It doesn't need storage because it produces it instantaneously, the hot water, right? Then another thing we talk about is the type of energy source, right? So there's gas, which is the cheapest. There's electric, which is usually the most efficient, although gas is coming up these days. And then there's solar. We'll not talk about solar because I haven't designed for solar before. But for gas and electric, most times electric is the most common, right? But if you have gas on site, so if you're designing for a project, you check if you have gas on site, right? So that gas is basically when there's piping, just like how you have piping for water, like a pipe network for water that supplies like the city or that region, right? So you check also if there's gas piping, right? Although gas usually introduces a level of, why gas may not be very common despite being cheap, because it introduces a level of safety, because gas leakages happen, right? But there's a lot of safety measures that are taken against that, right? So, and then as we go on, we also talk about gas piping, right? So you check, your other priority should be check if there's gas on plan. If there is, use a gas water heater, right? Along with the other gas equipment in the building. Then if there's no gas on plan, that's on the site plan, you now select your electric water heater. This one just goes with, you just connect it into your electric grid and your electric meter and all that, right? And then you notice that anything that has to do with heating consumes a lot of energy, right? So moving on. So redundancy has to do with, is usually more specified for commercial buildings. Redundancy is basically having an extra water heater in case one fails. Because like I always say, and as is reality, in public or commercial buildings, the standards are way higher, right? So some things that can let slide in your residential buildings can't slide in commercial. So nobody wants to hear that your kitchen or your restaurant is shutting down because your water heater is bad, right? So usually in cases like this, you need to have like an extra backup water heater. Or another thing you can do is that you can split the water demand into two, so that you have like two smaller water heaters as opposed to one, right? So that in case one is bad, and it can be connected in parallel most times. In case one is bad, the other one can serve until. So that's just what redundancy has to involves, right? So another commercial rule is that storage plus recovery is usually greater than the peak demand. So when you've calculated for the peak demand, you make sure that the storage of the water heater you're selecting and the recovery time is larger, is greater than that peak demand, so that at every point it is always more, not less. That you usually will have issue with undersizing, right? Although you get tempted to oversize, sure, but the best is usually slightly oversized, right? Then pumps too. So I spoke about domestic pumps, sorry, booster pumps, and then another type of pump used is hot water recirculation pumps. So this is usually used when we have a minimum distance of 50, right? 50 feet. Once you have your farthest fixture away from your water heater is 50 feet or more, you introduce your water heater, your water recirculation pumps, right? So usually when sizing for pumps, things you put into consideration are the flow rate, which is GPM, which is measured in GPM in this case, because flow rate is also measured in GPH, and I use GPH when I'm sizing for a tank water heater. But when talking about sizing this recirculation pump, I usually just stick with GPM, right? Because it's easier to find GPM values. If you notice, there was one table we just looked at where we saw the pressure here, pressure table. See GPM values are listed out here, right? Listed out here along with the pressure. So just read out those GPMs, and then your dynamic head. This dynamic head usually has to do with the amount of all the different things that would affect the pressure loss, right? The friction, the distance that the water has to flow over, and then the vertical distance, and so on and so forth. So you also need to put that into consideration when sizing. And then the efficiency. Efficiency, because the more efficient the equipment, the pump is, the less, the more economic it is, the less you spend, because you get more for the same rating. Then the control strategy most times I don't really have to bother about this, but it's something not on that. Control strategy has to do with how the thing turns on, if it's manually controlled or if it's automatic, and many different electronic mat matters, right? So other things you also consider in your design is valves. Okay, that's the end. So this one, I'll just need you to like read up on this because you already spent a lot of time on these notes, right? So read up on the pressure reducing valves and how they help to um, control balance flow in the building. Then backflow preventers, how the like the name implies, it is a valve that prevents backflow. And then check valves, which is basically one direction flow, isolation valves. I mean, all these things are all related, right? Then especially expansion tanks and water hammer arrestor. Please read up on these particular topics. So before we leave today, let's quickly look at a real life project or an actual project so that we can get more hands on, right? So what are we going to work on today? This is a project that we've worked on in the past, right? So this is that coffee shop, right? Okay. Ah, okay. So this is that coffee shop we worked on at the beginning of our class, right? So where we put our air handler somewhere here and then save this, save that. So you've done the mechanical plan for this project, right? Now let's talk about the plumbing plan, right? So let's look at the places. First of all, let's check all the available fixtures that require plumbing. So this is a cold room, no plumbing here, nothing here, right? But you see that there's a bathroom, right? Now this coffee shop, I had a back and forth with the client because I wanted to know why there were no other fixtures, because I feel like a coffee shop requires like more cooking fixtures. But this is like I'm sure they're going to give me feedback on that. But this is the available fixtures. So if ever you stumble across a case where for some reason, because and then there's this particular thing called mop sink. So for commercial buildings, and the bigger it is, the higher the demand for mop sink. So mop sink is like a type of sink that is used to wash mops and is used for like very dirty applications like cannot raise and wash in the kitchen sink, right? And it's usually like a standard compulsory for commercial buildings, right? So if ever the point of the importance of knowing about um, codes and standards is that if ever you spot something that is not correctly done, you can call attention to it. So in this project, this is just where we had our this thing needed, right? So now our plumbing fixtures needed. So now we have just the lavatory, and then we have the WC. So this is a small project, right? So then we just will decide where the water flows in from. Usually when you have to design plumbing for a project, if you have your site plan, right, or if you have more information, it's good to scan through the information you're provided with or ask questions. So because they usually need to tap their water off of a natural a grid, a water grid or water network, you need to know like where the closest water pipe is. But in a case where you don't have that information, just based on the building you have, just check where is best, right? And then if after designing, they might like call your attention that, oh, this is not where it comes in from, or this is where it's closest to, you now have to reroute, right? So sometimes to save yourself the stress, you might have to ask that question, right? Right. Although in many cases it may not really affect, but it just depends on how efficient you want to do your design. So this is this, right? So now I want my water to flow in through here and then supply this and then supply this, right? So let's design that. So let's draw pipes for this. I don't want to do this, okay? Let's draw pipes for this. So I already have my layers for that pipe, right? So I'll go to my cold water. My cold water. Mm, okay, this is my cold water layer. So see the color is here, the line type is here, and the line width also, right? And the line width is usually larger than. So I want my F8. I want to make it go at 90 degrees. So I want my piping to enter somewhere like this. Then I want my water heater to be mounted somewhere here. So that's why I brought it out here. And then this is my the only thing that requires hot water. So I would like to pass my pipe here, and then it will go up. Okay, because I want to adjust this. I want it to be somewhere here. Okay, okay. Now that is called like a snapping. That is snapping because I just hover the red and then it snapped to the point I wanted it to. So at this point now, at this point it entered from the ground into the wall. Right, this is an exterior wall. In this case, you don't have a choice but to use an exterior wall, and then it goes up into the ceiling, right? And then it goes still in the ceiling, and I use it and come and drop it here finally, because this is all that I think needs water. If I had other fixtures, I would have continued the routing, but this is where it ends. It's a very small project, right? So now, usually, oh, this should go. My cold water usually goes cold water is usually on the right, so this should be here. Okay, it should be here. Then I'll just continue lengthening to here, and then come here and then trim this. Okay, we are good to go. So next now is to do our hot water piping, right? So I go to my hot water. This is recirculation, but I don't need recirculation because this project doesn't have any up to 50 feet distance, right? So recirculation. Okay, sorry, hot water. Hot water. I want my heater to be somewhere here, right? So I'll just draw it. I don't want to use this shell, but okay, let me just use this small point. And so this is where it is. Or don't worry, I'll use something else. Don't want that. So let me just route the piping first. So my piping will hot water enters just here, right? And so I'll do my line. If you notice, by just changing the layer, changes like how I have to interact. And now, so I'll add. So this is just what the routing is. Simple routing, right? In our next class, I will do something more that has a lot of long distances. But let's just show you what it looks like at the end of the day, right? So this is it. This is what it should look like. Now, this is showing that we are getting water from the city, right? From the city, from the city's network of pipes, right? That is what this means. This just means continuity. So the pipe continues to wherever. That's now our business, right? And then this is our water meter. I've spoken about water meter a lot, and even in that pipe sizing um, um, table, you saw water meter size. So the pipe continues into here. Now this is our backflow preventer, right? Backflow preventer is a check valve. Is okay, not a check valve per se, but it prevents backflow, like the name implies. So it permits water in only one direction and not flowing back, right? Now, there are different types of backflow preventers. I would like you to look them up and then check why the applications for each of them, right? When they are used, because you will need to specify the type that you're using in cases, right? So, okay, let's move on. So, so this just indicates that pipe has gone up, right? Gone up. So these are just lines. These are schematic drawings, right? I mean, in Revit, it's usually more realistic, but this is just AutoCAD. So just use a line to show a pipe, right? And then this semicircle, this part circle, right? And it means that there's a pipe here that has gone up. So there's a vertical pipe. So it goes horizontally upward to this point and then it goes up, right? Into the wall, up through the wall, right? And then it also comes down to the height of this water heater, drops the water there, and then it continues. For water heater, the 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 location matters a lot, right? And then the size matters too. So go to, this is called a point of use water heater. I usually use this when the demand is very low. So in this case, the only demand for hot water is just this lavatory, right? So this shows the point where the piping enters the water heater, the supply, cold water supply for the water heater, and then this is where hot water leaves the water heater, right? So you see they are going parallel to each other, right? And then you see this pipe also means that it now enters that vertical, the vertical pipe that travels in the wall, right? And you see that the pipe continues its journey, right? The cold water continues its journey, comes here, it drops down into. Now I could have shown that this pipe to show that it is dropping into this place too, and that is what it should be actually, right? So I'll just copy this and use it there. Okay. So why I didn't do it initially was because, I mean, once the pipe has changed direction one time, means it is probably at that height. But let's just try and be, let's try not to leave out any necessary details, right? And then this is the point where it enters into the fixture, right? So then it continues its journey. It's in the ceiling now. I spoke about it in the ceiling, and then still in the ceiling, it gets down here and then drops down in a vertical pipe into the WC and then supply the WC. So there's supposed to be something like this, right? At the WC. And no, that is wrong. Okay, I want it to be at it, yes. So that just basically where the water enters the WC. So remember that we talk about SWSFU later. So this is just all that we need. This is a commercial building, right? That we need for that. Now let's go over the pages one after the other. Right. So this page one, our cover page, plumbing cover page, right? So we have our plumbing notes, which you familiarize yourself with. There's a lot of them. Some of them are referencing codes and other information that the contractor should know and you as engineer should know, right? This is usually built over time. So whenever something arises, you add it in your notes and then you usually like to avoid unnecessary errors, right? So now let's come to our table. So this is our fixture table. We'll talk about our WSF here. So for the lavatory, the quantity, WC quantity, and then we've read the WSFU from our table, right? Read the WC from our table. Now there are different types of WCs, but for this case, we're using a flush tank, right? And the different types have different WSFU values, right? So you just put your table and then fill in your values, right? So now you get your total cold water fixture units. Then you get your total for hot water. So if you notice now, there's no total for WC. So you continue and then total is this. Now you use this in your sizing, right? Now if you remember, we saw that for 100 feet and then okay, let's just look for that table basically. For 100 feet and 12.5 WSFU fixture unit, so that we need like a minimum of 3/4, right? So let's look for that for. Now this is our water sizing. Okay, um this is for IPC. Although our project is in California, right? But if you scan through this, there's a place that stated that we need a minimum size of this, right? So even if the That's 3/4, even if the demand is very low, like in this our case, 3/4 is still what we're going to use, right? So you see that let's measure our distance, right? So we need the maximum length, maximum distance, and then the maximum fixture units. Let's check that for our building, right? Okay, so let's go to our model, right? Okay, so let's measure the length from the water meter, right? So that is where it is usually measured from, because you don't know what this distance is, or you just measure from this, right? So this is still on the hot water layer. That's why it's showing like this. That's about 9 feet. So you press spacebar to repeat that same command. So this is about 4 feet. Press spacebar to repeat the command. I'm just trying to get the total pipe length, right? Press it again. Talking from here to here. Okay, this is about 2. This is 2 feet. Although normally this would have been in my dimension layer, but I don't have a layer for that actually. Dimension. But I don't really need it, so I'm just going to ignore. I don't really need it, right? Okay. Let's leave it. I'm going to delete these dimensions after. I just need to get this total length. Right. So the from here. Okay. This is right. So now I want to move this so that easier to calculate. Move it here. No. Okay, let's get our total length. Okay. So now we have 9 feet. 2 plus this is 4 feet, approximately 4 feet. 2 plus 4 is 6. This is 5 plus this. 6 plus 5 is already 11 inches. So this is about 5 plus 3, 8. This is about 9 feet also. So 9 feet plus 9 feet, which is here and here, plus 6 feet, that is 15. And then this is 16 plus 8, that's 24. So plus 9, that is 25, right? So this is a small, so it's 25 feet total. I don't need all of that. 25 feet total. So now let's go back to our table. Okay, we need CPC because it's a CPC product, but let's just check what this one says. So 25 feet at our WSF is what? Our fixture unit is, okay, no, this is not what we work on. Okay, this is a different project. Fixture unit is about 3 for the cold water, because hot water is less, so 3.5. Now let's go to, this is IPC. Let's just use the correct thing, which is plumbing, right? So we go to sizing, which is 10.4, right? And here is the next page. Okay, close this, don't need this. So now we see here that, okay, so 3.5 is our WSF, so somewhere here. So at 25 feet, so you see here 5 feet, right? So our sizing is going to be around 3/4. This 1/2. Let's see why that's the case. Right, because it stated, okay. You see here that it stated that in as much as they stated this for that very low demand, stated that is a minimum of 3/4. So it means for our pipe, it's going to be 3/4, right? Now let me show you how I usually indicate that. Okay. So sometimes I like to because I'm using the same type, I like to copy it from like a different file, right? To save myself the stress of having to create things like that from scratch, right? So this is what I need. Okay. I like to use Arial. So let's exit back to Arial. So hierarchy. Okay. Okay. Now that's more presentable. Do the same thing for this. Or I can use match property. Let's see. I'm just looking teaching you some commands. Okay, let's see match property. I want to match the property. It's not working in this case, and I wonder why. Usually, maybe I need to explode it first. Let's see. Okay, this is not part of our class, so. Oh, that is not what I wanted at all. But let's see if it works now. This is probably because it is a different type of element compared to this. Because usually, let's control Z that. Usually, once I press, you see, exploding has broken everything down. I don't need that, right? I want it to be the way it was. And it is back to the way it was. So match property usually it copies the properties to another element. I wonder why it's not working in this case, but let's not waste time on that. Let's just use our usual. Okay. Okay. So now I also don't need this under slab. Because I'm passing my pipe in the roof, right? On the ceiling rather. And then these two, I don't need those because so now I just need to position them accordingly, right? So one after the other. So I just move this. So this for the cold water line. I move it to my cold water, right? And then for my hot water, you see that this is already CW and HW. So for my hot water, so I'll just bring it down to the hot water part, which is somewhere here, right? So now I also want my work to look like very presentable. So I just move this down here, right? So that the work looks more, just make sure that there's a bit of alignment, right? It helps to make it look more professional. Right? It's not scattered. So this is enough. So this just basically means that my, okay, I remember this is 1 inch, so this should be 3/4 because of our demand, right? 3/4. Okay. 3/4. This. Okay. So this is according to our table, our table sizing. So minimum of 3/4, right? So let's just continue with that. So what else are we doing in this project? We've done our layout, right? So now let's look at page one. We've talked about page one, and this is the only table that is here, basically, right? And this is where I referenced the codes, right? That I used to show that I use California code, right? And then nothing much, nothing else. And then these are like some abbreviations and some legends, right? Images or symbols and their what they mean, right? You can go the extra mile and show the colors because we have like red for red for hot water and blue for cold water, right? So there'll be a time where we have recirculation too, but that is not today. Now, my next page, I'm going to show, I've added a viewport to show like my model, indicate it on my sheet, paper sheet, right? And this is it. And then remember this, we have our up notes, always have an up note, right? It helps like in interpretation of your drawings. And then our scale too. I'll show you how the scale is gotten. So let me show you immediately. So I come here, click paper, and now my, if I zoom in and out, it shows me other things here, right? And if you notice, this is basically to show how, if I click model, now the page doesn't move again, doesn't move. But if I click paper, Now anything I do here is as if I'm working on the model itself, right? So now if you notice also, because you can change the way it zooms in and out, you see that the scale here is changing. Now there are different preset scales, and the one that if you and if you select them, it shows you the one that you select the one that best sizes. Okay, this works. I mean everything is fitting to the page, but now it's clashing with some information I have on the sheet. So I want something smaller, which is this. So I mean you see how all that affects your presentation too, right? So now let's go over. So hey, now let's do our sizing of our water heater for this project, right? So we are working on GPH. There's this particular document I'm going to share with you, right? Yeah, I've opened it already. Yeah, we have information on water heater sizing. Let me fix this. Okay, yes, this is it. So the name of the document is Design Considerations for Hot Water Plumbing. Right. I only need this because it's usually mostly GPM values are found on um the codes, right? So I mean in another of our class I'll show you how GPM water heater sizing works. Right? So this just gives us like the GPH for different fixtures in different types of buildings, right? So in our case we just need a basic lavatory, right? Okay, this is our building. Our building is just a small coffee shop. So this is okay. Let's scroll down. This page it, but let's scroll down and see. There's another table I saw. Okay, let me zoom in so you can see better. Okay, apartment, club, gymnasium. Right, right. So this is a private residence, right? So why there's so much difference between residential and commercial is because the demand is usually way less for private, right? And then way more for commercial buildings. If you notice now, see these are the different brands. Let's go for a lavatory. Okay. Lavatory, lavatory. Do we have a lavatory? Okay, this is this lavatory. Now for a public lavatory, we have, if you notice the value changes. See, now this is a private lavatory too, and this is equal across all because private is usually for residential, right? Or like just see demand is very low, but when it gets private and public, depending on what type of building it is, it increases for commercial applications, and it's the highest for industrial. See how high it is for a school because of the population, right? These are GPH values, right? So now all we need is just um GBH for just a public lab, a basic public laboratory, which is this is for an apartment house. And which one do we choose? Now our building is just a basic um coffee shop. So I mean the population is going to be a bit high. So I feel like we can model it after not an office building, a club because people are coming in and going out, right? And so then so we're just gonna take 6, right? So I did this. This should be 6 and GPH. This I'm using GPH because I'm sizing for for the tank water heater, right? Although the volume is going to be quite small. So which is total of 6 too, because that's the only um fixture that requires hot water. Right. So now I have my water heater template. So I have one for tankless, which we'll use eventually, and I will use it with GPM. Then I have one for tank, which is GPH, and I even have one for steel tank but gas, right? Remember we talk about electrical and gas water heaters, right? So in this case, there's no gas on plant, just uh, a basic electric water heater, right? So put in my total GPH demand, and it gives me that I will need, okay, this elevation is just basically the highest um point in the building where the hot water is needed, and in our case it's just a lavatory which is about 4 feet above the ground. If there was a shower, it could have been higher, like maybe like 6 feet or, yeah, or 7 feet, right? So what we need here is just the total GPH and then the kilowatt rating, because um is a very low. So this kilowatt rating is just shows like the electric element that is needed for heating that water, that water heater. So this is what we use to select our water heater. So simply look for um a, a because our demand is quite low, so we need a very small water heater. So if you simply search on ChatGPT or on Google, search for a water heater that can accommodate this kilowatt rating of heating, and basically this rating is just showing, it shows how much heat, how much electricity is needed per time, right? Which is still gallons per time to heat up this gallon per time, right? So, right, so these 25 gallons, we don't need it for this project because this, I set it as a minimum of 25, because for bigger projects we need like a maximum of 25, because if I want to like increase the number of gallons or the number of water heaters, I set it as like, we don't need it, let's just leave it, we don't need it. When we need it to talk more about it, right? So this is, so simply look up a water heater that can handle this, right? So I just simply searched for a point of use tank water heater. Point of use is usually of small, it's a small value, right? Okay, let's just search and can do it in real time. Yeah, we'll do that another day. Time is on our side today. So for our next project, we'll probably do that. Right. So I have like a template where I have like some water heaters that I've set. So in this case now, it's telling us that we need, these are the details, right? So if you notice that our template showed us that we need a minimum of 1.28 kilowatts, and I found the water heater that can work with 1.44, and this means it can comfortably sustain it, right? And then it's 4 gallons, right? But I need something even smaller. For this 4 gallons, I selected it based on if that water supply was up to 12 GPH. If you remember in our here, we had even higher for that public lavatory, we had up to 12, 15. So I mean, for such a project, we have like our, this is being like times 2, right? So for this, I'm confident that this water heater can supply, right? So this is the details of the water heater, all of that, right? And I'm sure even a smaller one should be able to cater for it. So another assignment for you is to kind of check, because in my template I have a smaller one. This one is 2.5 gallons. Check if this one can accommodate for our 6 GPH, right, for our lavatory, right? So that is pretty much. Let's see if we can look at another project, although I doubt. Now we are done with this page. Now let's look for the next page. This next page talks about the drainage drawing, but we are not talking about this week. So look at it next week. So now next thing that we need to specify is, it's called a riser layout. So riser layout basically provides us with um our water supply, our piping, or our design at a glance. Right, just like a small drawing. And this was done on the main model page here, and I brought it in here through this. And it just shows us that, okay, this is our floor level, this is where the water travels in the ceiling, just under the roof, and then this is the supply. I mean, this could have come down here, but let's just leave it here because just because. So this we can even edit here. If I go to paper, I can edit this to 314. And this 314. Right, okay. This you notice this is a different type of fraction. I'll just edit it how I want it to be stacked. Right. I want it to be horizontal. Right. Okay. Okay, I see what happened here. In this case, I did not even stack it. I just put 3/4 and left it. Right. So, but this should be deleted. It's not necessary. So, no. Because this is useful for when you have. This is useful for. Hey, I'm shifting this in a lot. Shifting it a lot. Okay. Okay, as far as I don't zoom in on that, no issue. Right. So this means it's covering for both at the same time. So in this case, I don't need this type because I want it to just be on just one. I'll just copy this one. Copy. Move it from here. Somewhere here. Maybe. Right. Oh, I probably don't even need it, right? Because this shows that it's covering all of these points, right? I go back to my model and zoom. So now it just basically shows us, okay, this is our point of result enter. And this just shows us how it's connected, right? And then so as the water flows in, it enters the water heater first, right? And then after water heater, we now have the water going out and entering into the lavatory, right? So this same main line, distribution line, supplies this, which is the lavatory, and then supplies the WC as well. Right, you see all of them is 3/4, 3/4. So that's the minimum pipe size. But if for any reason you have to supply more um more fixtures, the size will increase according to the table, right? So it's only when it's exit. Let's even go to that table and look at it, right? So as you can see here, so before we get to one, right, this is the main supply branch, main supply pipe. Before we get here, we need to need a maximum of 29 at 29 fixture units at 40 feet, maximum of 40 feet, or if you are getting to 60 feet, 25, just like that. So this is this fixture unit, so right. So anything less than this will still go with a 3/4. But I start talking about going for even bigger pipes, see that the demand is increasing, fixture units are increasing accordingly. Right? So don't just because it increased from 3.5 to maybe 6, and start changing it, right? You change it according to what the table says, right? So to continue. I mean, in our next class, we'll talk about a bigger project and we why don't we do that today? Right? We can always look at, or let me just, or we can always look at another project, another class, so we don't have an extremely long class today. So anything that is done here can always be easily expanded on, right? So I think we are pretty much done for today. So thank you for tuning in. Right, and I'll see you next time. Okay, let me just look at everything else. Okay, look at everything else. Okay, we'll talk about this on our next class. This is just our detail, just like how our detail page in M for HVAC drawing. So thank you for tuning in and I'll see you again next class.